So in this next video, I'm going to be going over some component selection, and hopefully this will be the last video in order to build a boost converter, at least up until the basic design, as opposed to designing, particular things. So the first thing we're going to do is, well, the first thing I've done is I've actually simulated this. So here is in a demo version of PSIM. And the values that I've chosen here are just again from the spreadsheet. So we've gone through and similar to the values we've used before, voltage in, voltage out, 100 kilohertz switching frequency, and our power. 2% voltage ripple, 20% current ripple, and that gives us these values for the components. So I've entered them in here, 336 for the microhenries for the inductor, and 4.2 microfarads for the capacitor. And then for the resistor, I've just taken the output voltage squared divided by the power, which gave that. So this is at 240 watts. This is 210 watts, but I've amped the power up because our efficiency is lower than that. So this should just give us a general idea. All these are ideal components right now. And what that looks like is this. So this is the voltage waveform. See, it's plus or minus about a volt. So that's good, 2%. Then the current is about plus or minus 0.4, total of 0.8, which is, again, that 20% of the 4 amps average for the current. So that's good. The thing is behaving how we want it to. But these are all ideal values, and so we'll talk about kind of the component selection now in more detail. Starting with the capacitor. So the capacitor is 4.2 microfarads. How do we select a capacitor type? There's all these different types of capacitors. The general thing you can do is just using some sort of table like this. Usually it's pretty obvious if you're using low values and low voltages, then you can start to use just these ceramic. But as you push up in capacitance and up in voltage, we start to look at these different types here. We're at, again, 4.2 microfarads. So that's around here-ish, and we're looking at around 100 volts. So that kind of has this little intersection here where we have aluminum electrolytic capacitors, plastic film capacitors, and ceramic capacitors. And maybe these power capacitors as well, but let's stick with these three first because these are kind of most common types of capacitors. And what I'll do is I'll just try and look at like some selection for each of them. I think there's a lot of research and like stuff that can be done into this, but I'll just talk about the little that I know about selecting these capacitors. So we'll just go through them each. Since we can use any of these three, we'll just take a look at all of them. So let's start with the aluminum electrolytic capacitors. So here on DigiKey, I've just gone through and I've picked up a capacitance value of 3.9 to 4.7 microfarads. So that includes 3.9 is like one of the most common, and 4.7, and then 4 is kind of less common. So hopefully 3.9 and 4.7 will kind of be that range that we're looking at. And I've rated for above 100 volts, and I've made it in stock and normally stocking. And here we can see we have lots of options for these. These are aluminum electrolytic capacitors. Lots of options, plenty of things to look at. So this is good because we have lots of options, but we can start to look at like what these power losses might be. So let's just take like a 63-cent one here. And I've pulled the data sheet for that one. So this is that one. So these are rated for like very high voltages. So we don't have to worry about the voltage, and the capacitance is 4.7, so that's fine. The thing that we're interested in here is the dissipation factor. So while we're trying to find the the equivalent series resistance. And if we look here, that's what we need in order to calculate our capacitor losses. So the value I have in here is like 0.024 ohms. However, this doesn't give us an equivalent series resistance. The value that it gives us is a dissipation factor, or a tan delta. So it turns out that the tan delta is actually just this. So this is kind of our real component and our complex component, and our total impedance. So if we know our total impedance, we can get the ESR from our tan delta. And it turns out it's just this formula here. So ESR is tan delta divided by 2 pi times the frequency times the capacitance. And this frequency is not the frequency that we're operating at. It's the frequency that they tested the tan delta at. So if we go back to the data sheet, we can see that we have at 400, which is what the one that we're looking at is rated for, we have a 0.24 tan delta at 120 hertz. So we can enter that into our sheet here. 0.24 at 120 hertz is 75 ohms. This is really high. So this, if we enter this into here, 75.79 ohms gets ESR loss of 22 watts, which is insane. That brings our efficiency from like 98 down to 88%. I'm not actually sure if these, like how accurate these are, but it definitely means that, and we see this if you go through and you look at the other ones, a couple of them have the ESR here, and it's in the range of around 30 ohms. So we can see that the problem with aluminum electrolytic is that even though there's lots of options and they're very highly voltage rating and they're pretty cheap, their ESR is quite high. Even at like 30 ohms, that's going to be 8 watts of power loss, which brings us down to 95% efficiency. So these might be possible if there's a better way to calculate the ESR, maybe at higher frequencies. The formula doesn't apply, but as far as I can tell, aluminum electrolytic are a little bit too inefficient for what we're looking at. So let's look at the next option here, which is these plastic film capacitors. So plastic film capacitors, I've gone here. So on DigiKey, they're called film capacitors. And in stock, normally stocking, voltage rating from 100 plus, capacitance 3.9 to 4.7. And we can see here, again, we have a good amount of options, but instantly it becomes obvious that these are more expensive. And this might be okay if we're only using a couple. We can see that they're all kind of range of voltages. Again, like very high voltage ratings. And, they're a little bit more expensive, but they're not going to break the bank. So let's try and look at the ESR for these as well. And here, you can see that a lot of them aren't posted here. If I just sort it from bottom up, we have in the milliohms range. So around 14.7. Oh, sorry, that's down. Here we go. You can get them as low as around like 3 or 4 milliohms, which is really good. This means that we can actually use these. Let's go into one of these data sheets of a higher stocked option like this one. And we look and just verify this. So Control F, ESR. We can see that an ESR in milliohms at 10 kilohertz. So that's within the range that we're dealing with. We'll look for like a 4.7 is around 8 milliohms. So that's a lot better. If we throw that in here, we go 8 milliohms. Here we go. Now we're seeing very, very low capacitor losses. This is more reasonable. It's not really going to affect our efficiency. Actually, even if we go up to around, say like 30 milliohms, we're still not really affecting our efficiency here. So film capacitors to me seem like a good option. Any of these seem all right. They have the right frequency, voltage rating, that kind of thing. I won't pick a specific one, but definitely there's options in here that seem good. So we could stop there, but let's quickly look at the ceramic capacitors. If we go into ceramic capacitors, we see that there's the biggest advantage straight off the bat is just that these are really cheap. You can get like $1 for a ceramic capacitor. And generally, these are cheaper than the film capacitors. Not exclusively, but generally they're cheaper. And we can go into one of these. They're these surface mount. They're much smaller. They do have lower voltage ratings. You have to be careful here. 100 volts maybe is okay for this, but if we want to overrate it, we might want to put a little bit higher voltage on this. We'll have to choose a little bit larger of a capacitor. And these don't go to as high voltage, as you can just kind of see by here. These capacitors at the microfarads that we're working at, we're in the range, but definitely they're limited a little more than these plastic film capacitors. But if we look at this, we want to estimate the equivalent series resistance. We can actually look here for ESR. There's nothing. For tan delta, there's nothing. And it turns out that the ESR for these is just really low. In general, for ceramic capacitors, the ESR is just very low. So for this specific application, these might be okay. The thing is, if we're going with higher capacitances, we might have to stack a few of these, or higher voltages, they might not work. We might have to go to film or aluminum. But as far as I can tell, these seem like the way to go for now. Either these or maybe a film capacitor seem like the best option for capacitors. So the next thing we're going to look at here is the inductor, 336 microhenries. And that again comes from our sheet here. So right here, 336 microhenries. I know that these are around 330 microhenries, but I'll just put a range of, I think, 300 to 400. You kind of want to leave these ranges pretty large because there's set values that are good and set values that are more common and less common. And you kind of want to find one that's more common. They'll be cheaper. Current rating, minimum 5 amps, in stock, normally stocking. And we'll just run down them. So here, the thing we're going to be looking for, we can start by, is our, where is it? Oh, they don't have DCR. Okay, well, we'll look in the thing. So, we can even see them here. 64 milliohm, 50 milliohm. We can kind of get an idea of, they're in the tens of milliohms kind of range. So let's look at ones that are higher value here, just more available. So 300 microhenries, that's fine. We're at 64 milliohms. Let's pull this up. Yeah, so saturation current at around 10 amps. So that's above the amperage that we're working with. Again, the amperage here. Works way up to about 4.4. And if I zoom entirely out, we can see that it gets past 10, but not that much past 10. So a saturation of 10 is okay. DCR, here we go. So we're looking at different inductances here. Microhenries, we were at, I think, 300? 300, yes. So let's look for that one. Here it is, 364. So that's about what it said here, 64 milliohms. We can throw that in here. So 64 milliohms. And we see that our inductor losses are around 0.8 watts. So this is more significant. And we don't have the AC core losses yet. So instantly we can see that our inductor losses matter more than our capacitor losses. So when we're choosing the capacitor, we can kind of just pick something that's good for our application and don't worry as much about the losses. Again, as long as we're not using that aluminum one. The inductor losses can be quite significant. So minimizing this might be a little bit better. So we can go back and actually, let's see. Oh, here we go. DC resistance. Ramp this up. Sort of ascending. And we can see that the lower ones are around 20 to 30. So let's throw in 30. Throw in 30 here. And we have inductor losses of around 0.38 watts. So we can see that there are definitely good options here for buying inductors. One thing to note is that a lot of times people in power electronics don't like to buy their inductors. They prefer to actually just build their inductors. So you'll buy a core, and you'll buy some metallic wire, and you'll wrap it around and you'll put it on some base. This might be a good option too. I think if you're just building something right off the bat, don't go for that. But if you're, wanting to do the hyper efficient, get something very precise, then definitely worth building something yourself. Also, you can see that these are very expensive. The cheapest ones, the cheapest ones range in essence of like a few bucks for that kind of one that we are looking at before. That's 64. And I think if you're trying to go to the more efficient, lower resistance types, they start to get more expensive, like in the tens of dollars up into like $50 kind of range. So there's definitely options here, but again, like a lot of people like to build them themselves. You build your own inductor, your power inductor, and you run with that instead of trying to just select one. But you definitely can select them, and these would kind of be your losses. You'd be looking at something like one of these ones that's more common. That's the one that we're looking at here. Not too much about it, just make sure your current rating is fine and that your saturation current doesn't exceed whatever your max current is going to be approximating. Otherwise, your voltage is going to spike. So the next thing here is going to be the diode. We're just going to select this diode. Basically, just pick something that's going to work for our application and try and minimize our losses as best as we can. But our diode tends to be just our forward voltage that we're looking at. So just minimizing the forward voltage and everything else we're not too worried about, but we can look for things that are excessive. So let's start by just going to DigiKey, searching diode, and we have single diodes and single Zener diodes. We're just looking for a diode. So we can run through here, and I just put in a current rating of basically at least 10 amps. Wanted to be a bit excessive there. And reverse voltage. So this reverse voltage is just going to be the output voltage. So when the switch is closed, this diode has to withstand a total of whatever the output voltage is across it. And again, for the forward current, I just picked 10 amps because I like to overrate these diodes. And I tend to find that, you have a lot of spiky currents on it, so you don't want to underrate them. So you could probably go less than this, but anyways, for now, this is fine. Look at some of these here. Sorry, never mind. I did go lower. I went down to 9 amps. I don't know why it's going here. Okay, yeah, so I did set the minimum to be 5 amps. Anyways, we're looking through here, and we're looking based on our forward voltage. And we can see that there's a lot of options here around 1 volt. If we sort from the bottom up, we can see that around 0.7 volts is definitely our minimum that we're looking at. Especially with these higher currents, you can't really get the super low voltage drop. But these are pretty cheap, and generally these are going to be the Schottky diodes that you're looking at. So any of these will seem kind of fine to me. 76 cents, not too bad. 120 volts reverse, average current 8 and 760 millivolts. So let's pop that in here. And our forward voltage 76. Okay, looks like I already did this one. And I can throw in the other stuff too, the leakage current, TRR, IRM. But I'm going to leave that out for now because I just want to do kind of quick pass. But that'll all, again, be in the data sheet, and you can go through your calculation to find your switching losses. So the next thing we're going to look at here is MOSFETs. Again, we're choosing a MOSFET, and we need to look at the rise time and the fall time, the RDS, and the leakage current. Look at a couple of the values or what's happening with this MOSFET. We have a voltage that's going to be when this diode is conducting. It's going to be just under 100 volts across it at its kind of peak, 101, 102 maybe with that 2% ripple. However, the startup, the voltage may be higher. And that's actually something that I should probably mention, is that this voltage does briefly exceed that. So we need to make sure that they can exceed their max voltage for brief times, but generally we want to be overrating these things because of stuff like this. When you're initially starting it up, you might have these excessively high voltages. Anyways, so let's look at DigiKey again. And we just went through, so there's P channel and N channel. When we talk about MOSFETs, usually we're talking about N channel just because they're more efficient. So yeah, we'll use those. No reason not to. The current, here we're looking at a maximum kind of current that's going to be running through here of whatever the maximum current that's running through the inductor is, which again we see here doesn't really exceed much above 5 amps for any significant amount of time. So 5 amps is the number that I'm going to consider. I think I overrated it a little bit, but you can see here 6.3 amps, 5 amps. There's lots of options here that meet those requirements. And 100 volts, drain to source, and in stock, normally stocking. So a lot of these are good options, but again, we're kind of looking for the minimal rise and fall time and a minimal RDS, as well as a minimal leakage current. And we can see here our switching losses account for just over 50%, and our on losses, which are our RDS losses, account for most of the other losses, whereas our off, that's our leakage current and stuff, don't really matter that much. So let's just pull up a example of what we're kind of looking at here. Here it gives you a few things. So let's start with our RDS on. So at around 2 amps, we're at 155 milliohms, 140, 1.5 ohms, 54. So you can see these vary quite a bit depending on what current we're running through them. So around 4 amps is what we're looking at for our 66 milliohms. There's a lot of different things to look at here. So let's sort this and just look for one that's pretty low, but in our range. So 54 milliohms at 10 volts. So this 10 volts is not the VDS. This is our drive current, drive voltage, sorry. So 54 milliohms. Yeah, this one looks okay. So let's take a look at this one. And we see it's the surface mount type. Open the data sheet. Yeah, okay. So our continuous drain current, and we see at different temperatures, this will vary, but it's definitely above this sort of, even when we're running pretty hot, the max current can still handle like 4.2 amps. So that's definitely within our rating. We go with the thermal resistance ratings. You can look a little bit more into these. This is basically how it's going to dissipate heat as a function of power. So these power MOSFETs will dissipate heat, and oftentimes you'll see them with like a big heat sink on top. This will tell you a lower thermal resistance means it can sort of dissipate more heat into the air. But what we can do is look at, okay, here we go. VDS is about 100 volts, that's fine. And we look at two different gate to source voltages and two different RDS ons. So let's just use an average number, so 0.06 for our RDS, 0.07, let's go 0.06. And there's a couple other useful things here, but let's ignore those for now. What is the other value we're looking for? Rise and fall times. So we can go down here. Rise. There we go. So our dynamic behaviors, our gate resistance, etc., etc. Here we go. Rise time and fall time. Looks like we have two different parameters that they tested at here. 4 amps. Oh, okay, so they're either running it with 7.5 volts or 10 volts. So we'll just choose the average there. I don't want to get too much into that. And we see that our rise time is in the 5 to 10 nanosecond range, and our fall time is in the 5 to 10 nanosecond range. So we can pop those in here. So these are nanoseconds. So let's go 7.5 and a fall time of 7.5 nanoseconds. And then we can add the leakage current as well. Leakage 100 nanoamps. So 100 nanoamps is like 0.1 microamps. There we go. We have our total losses. So again, our switching losses make up the majority. Our on losses a little bit less. That brings our total to about 0.8 watts. So a little bit less than the diode, which is important to note. Our diode is kind of like our focus if we want to reduce our power usage. Yeah, but that's a MOSFET. The other thing I want to look at is the power dissipation. Maximum power dissipation. So this, I'm not sure what these different values are here, but let's take these top numbers here. So at 70 degrees or 25 degrees, we have 15 to 24 watts that it can dissipate. So does that make sense for our converter? Yeah, we're not running it higher than about 1 watt. So we can definitely use this, and it's not going to blow up. We don't need to add any excessive heat shrinks or anything. If we were running more power through it, that's where we'd start to need more heat sinks, and we can start to calculate out with the thermal resistances and things like that. But for now, this looks like a good option. There's plenty around this range. If you're worried about the voltages, you can just run a slightly higher voltage, and there are plenty with a little bit higher voltage ratings. 700 volts, 600 volts, 600 volts, 200 volts, a lot of different options here. So just go through and look for one that's reasonable in the range that you're looking at. But again, that RDS on and the rise and fall time are the things that you're going to be looking at. So one last thing with the MOSFET is we need to send it this signal. So this PWM signal, 100 kilohertz, 0.4 duty cycle. And you might think, okay, fine, I can generate that with a microcontroller. Yes, you can generate 100 kilohertz, 0.4 duty cycle. But the problem with MOSFETs is you'll need to power it with something more than a 3.3 or a 5 volt output. This is 10 volts or 7.5 volts on the data sheet that you need. This is the one of the MOSFETs that I was looking at. So, we need 7.5 or 10 volt PWM signal. And that maybe isn't a problem if you have a microcontroller that can output 10 volts, but you definitely don't. You have one that can output 3.3 volts. So you need something that sits in between your microcontroller and your MOSFET. The things that we're going to use are called these gate drivers. So let's just pull up one of these. This is a MOSFET driver or gate drivers. And there's two types depending on your configuration. There's low side or high side. So this just depends on which side your source is connected to. So this is our MOSFETs. I don't have a signal, but this is your source, this is your drain, this is your gate. So if your source is connected to the low side, your ground, then you need a low side driver. And if the source is connected to the high side, you need a high side driver. So in our case, it's a low side driver. And we need it to do a few things. We need it to output a certain amount of speed. We need to output a certain amount of current and a certain amount of voltage. So we can kind of go to this and look at kind of what these things will be. So in our case, our VGS is either 7.5 or 10 volts. We're going to choose 10 volts because we want a lower on resistance. And you can see here, this curve with 10 volts is a lower on resistance. So we need 10 volts, and we also want to look at the input current, which I can't find right now. I think you find it with the gate charge. I'm not too sure about this actually. Yeah, you do have some gate charge here. I think you can calculate basically the amount of current it'll need, but I think this gate driver will be okay. And we look at the data sheet. We find it can operate on 3 volts to 11 volts. Can take reverse current, that's fine. Protected against ESD, that's great. Output current is 1.5, that'll be more than enough. Our output current of our MOSFET is not more than like 5 amps, so that's okay. Low supply current, withstand swings up to 5 volts, that's fine. 4.44 nanosecond delay times. That's fine for our application. 100 kilohertz is pretty low frequency, so we're able to deal with that. There's other stuff you can look at here for how this is going to control our MOSFET. I would say just look online for a MOSFET and a gate controller that seem to be popular, but I just chose this one. There's lots of options here where you can go through. They're around a few dollars, but basically you'll need one of these in order to drive that MOSFET. The other thing that you're going to need to consider with these is that they're driving a higher voltage, so you have to power them somehow. So I'd also recommend adding a smaller buck converter. So this is your overall boost converter, but in order to operate this switch, we have 60 volts, and you can take the voltage here and just step this down using a buck, just like efficient, one of the ones you buy on DigiKey, to power our thing that's going to power the gate. So that'll provide the voltage to our IC that's going to sit between, like, our microcontroller is going to output a PWM signal, our buck is going to connect the power, and then this will output sort of the higher voltage PWM signal to this. Hopefully I've gotten everything. Again, I'm not 100% sure. So if you're watching this and you're not from UBC Solar, or you are from UBC Solar, I just made these videos as sort of a guideline for how I might design a boost converter. But I am by no means an expert. This is kind of just me figuring it out on the fly and hopefully saving you some time going through these things. But yeah, inductor, we went over, you choose one, you wind one yourself. Diode, again, you just kind of choose one. we'll need the MOSFETs. We'll pick one that's for the select ratings, and we'll make sure that we have a buck converter to supply the power, or some sort of power supply to the gate driver, which you'll also need to select, and that'll be between the microcontroller and the gate driver. The other thing that we're going to need is probably a voltage sensor at the output. It would be nice to have this. So if you have the voltage sensor at the output, you can basically make sure that this is outputting the voltage that you want it to do. And we can add a little bit of a feedback in there. I know that you've probably already dealt with some simple voltage sensors. You can also just do a voltage divider down into some microcontroller pin. But it would be nice to, on a PCB, have the voltage sensing capability. And then in your software, you can adjust your duty cycle, things like that. Yeah, that should cover everything. So you have your capacitor, your diode, your inductor. Those are all just your passive components that you're selecting. The load will be an external load. The source will be a power supply that you're running. Make sure your traces are rated for the right current. Your MOSFET you're going to select, and then you're going to have a gate driver for your microcontroller. You're going to have your microcontroller basic peripherals, and some sort of voltage sensor on the output that you can send back into the feedback loop. And as you saw, like some of these components can be quite expensive. The inductor, especially, in the dollars of range. The gate driver and MOSFET can be kind of expensive. Capacitors usually pretty cheap, but overall, this board with relatively few components hopefully won't be more than like $20. These power electronics boards can be more expensive, especially if you try and run more efficiently. Anyways, I hope this video was useful.